proximal decomposition. So as you already see, in many, many cases, the key fact is to be able to compute the proximity operator. As we show, if you have one norm, for instance, why one norm is so useful? Because it yields sparsity, because you can compute its proximity operator in closed form, right? It's just a shrinkage operator. So it's so convenient. So therefore, if you are going to design a different regularizer than the L1 norm, you will need to be able to compute the proximity operator of that. And for that, we need to study the proximity operator, more carefully, and hopefully we'll find some rules how do we compute the proximity operator. And this is going to be a very simple result. So now, let's say we have two functions, f and g. These are just two regularizers. Okay, this is the one norm, this is the no rank, say the trace norm. Okay? And you want to have both of them in your application. You want to have both structures. That's why you take the sum. Well, it's debatable. Maybe you can take a max, maybe you can take other things. But let's agree for now, we take the sum of the two regularizers. Okay? This gives me a new regularizer. So now, if I'm going to apply the proximal gradient algorithm, which so very popular, we'll discuss later, we will need to be able to compute the proximity operator. By the way, there are many, many other algorithms, not just the proximal gradient algorithm, like the ADMM, alternating direction method of multipliers. You also need to compute the proximity operator. So this one is really the key of a bunch of algorithms. So we need to be able to compute the proximity operator here. So that's P F plus G. So for simplicity, I'll just ignore the either here. How do we compute this thing here? Well, because we choose two structures, right? Two regularizers. Probably we know how to compute the PF, and probably we know how to compute the P of G. Can we leverage on the fact that we can compute these two guys and to compute the sum? Well, if we have this, that would be awesome, right? We just take the sum, but that's not true. Very unfortunate. And as a matter of fact, there is a closed form. There is an analytic formula for you. And the formula is this. It's not hard to prove. P2 of F, take the inverse of this. Because this is a 1-1 map. You can show the proximity operator is a 1-1 and onto map. It's a bijection, essentially. That's why you can take the inverse. P2 of G inverse. And take the inverse again, and then you compose with identity map. Okay? Or maybe let's write it in an easier way. Divide by 2. Okay? This is the analytic formula, exact formula for you. The only trouble is you need to invert these maps. Well, inverting this map one time is not a big problem. You take the sum, and then you invert it again, right? This will be very, very troublesome. So we don't know how to do that in many, many applications. We don't know how to do that. Even though this is a nice formula, we don't know how to do that. So this is known as the parallel sum. I think it's from physics. In particular, if these are matrices, it's called a parallel sum of two matrices. So this is the dead end. We cannot use this formula even though it's nice. Well, on the other hand, we do have some successful stories. One is called the Fuse-Nassau. In this case, F is just the 1 norm. G is going to be the total variation norm, okay, which is defined. Okay, let's put the argument here. Sum I goes from 1 to d minus 1 xi minus xi plus 1. Absolutely. So this one gives me sparsity. This one gives me continuity. Essentially, I want a signal to be piecewise constant, right? So this is the Fuse-Nassau. It's proposed by Chip Shrani and his co-authors, I think in 2005. At the time, they don't know how to compute that thing. At the time, they don't know how to compute 1 norm plus total variation. 2 years later, they come up with a very beautiful solution, which essentially says this is going to be the proximal map of the one norm compose proximal map of the total variation norm. So compose means, if I want to have Z here, composition is just, you apply this first, and then you pass onto the one norm. Okay, this is what I mean by composition. So this is really a beautiful result because we know how to compute the proximity operator for the one norm. It's just a shrinkage operator. For the total variation norm, because of this snide coupling here, it's a little bit more troublesome. But again, you can show using a technique of dynamic programming, this one can be computed exactly in linear time. So again, both of them can be computed in linear time exactly. Therefore, we can compute the sum exactly in linear time. It's very nice, right? Okay, another result from Frank Sparks' group, they proved that it's called the tree structured group lasso. Well, but on the other hand, proving this result in the original paper is not easy. They need to analyze, use convex analysis to analyze the whole thing in pages and pages. But later on we'll see it's really an easier result. So tree structured group result, group lasso. So what is tree structured group lasso? So essentially you have your features, okay? And you arrange your features in a tree. So for instance, you have your feature 1, you have a feature 2, feature 3, and maybe you have feature 4. Doesn't have to be a binary tree. 5, 7, okay? These are your features. You arrange them in a tree. And what are the groups? So now the groups is, you take a subtree. From the root, you take a subtree. This is going to be a grouping of your variables. Take another subtree. This is another group of your variables, okay? So this is how you derive the groups from a tree. So essentially, you're assuming your variables have a hierarchy, and you encode the hierarchy with these groups. Like you want to group a certain, you want to group some variables together. And the result is this. It's very similar to that. So essentially, you take the proximal map of a sum. Let's just take two groups. Okay, the first group and the second group is going to be the proximal map of the first group compose the proximal map of the second group, provided that G1 is subset of G2, or G1 intersect G2 equals empty. So this condition is why they need the tree structure assumption. So essentially, if you know combinatorics, you will realize that this tree structure is nothing but the so-called laminar system. So for any two groups in this tree, either they don't intersect, okay, or one is contained in the other. That's the key property they use to prove this result. So both of these results seem to imply that if you have two functions, the proximity operator of the sum is just a composition of the two proximity operators. That seems to be the observation, and it's to me, right? So let's just try to make this rigorous. Is it true or not? If it's not true, under what conditions it is true, right? At least we have two positive examples here. Okay. The quick answer is it's not true. You can build natural counterexamples to show that it's not true. So, short answer, not true. And by not true, I mean PF plus G is not equal to PF compose PG. Okay? The next step will be, under what conditions this can be made true. Of course, we need lose natural condition for that. So the first, so I will state this as a theorem, even though this is a really trivial result. So the idea is quite simple. We have 3 proximity operators here, right? And we want to combine them. Well, all we need to do is we take the derivative in the definition of the proximity operator. Nothing fancy. Just take the derivative, apply the optimality condition. So for the first guy, PF, we know for the first guy, PF plus G, we know PF plus G of Z, because it's optimal, minus Z is going to be in the subdifferential, plus the subdifferential of F plus T, evaluated at the point. It's going to be a little bit messy, but really it's just taking the derivative, nothing fancy. So 0 is there, okay? Just take the derivative in the definition of this thing here. Take the derivative, you get this equation, nothing fancy. And for this one, similarly, you can prove 0 is in, well, not prove, but just apply the optimality condition. Minus Z plus partial G of P G of Z. So this one is this, that's that. And we have this PF here. Then 0 is in P F PG of Z minus PG of Z plus the subdifferential of PF PG of Z. Okay? It's just the proximity operator at that point. Again, set the derivative to 0, you get these 3 optimality conditions. Nothing really fancy. And now the observation is, well, we have these 2 equalities here. Just add them together and see what happens, because you have this term here and you have this term here, right? If you add them together, they cancel. That's a nice thing. So we just add them. We get the PF. This one remains PG of Z. And then we have the minus there, and then we have these 2 terms. Okay? Very simple, naive even. So now we don't have these 2 equations, because we have added them together. These characterize one we want. This is what we obtain from PF and PG. So we just compare these 2. Okay? Because these guys are the same, this one is almost the same, but not quite. And these guys, they're not the same. Well, that's where we make assumptions. Right? We assume they're the same, and then we get equality. So the assumption is this. Assuming for OY, if partial G of PF of Y contains partial G of Y. So essentially this theorem says, if I apply the proximity operator of F, I will enlarge the subdifferential of G. Okay, this is how F and G interact. It's not very intuitive, but this is basically what this equation says. Apply the proximity of map of F, then I look at the subdifferential of G. It becomes larger. That's basically this condition says. Well, if you have this, and let's see. So this one, under very loose conditions, you have this. This is not always true. The subdifferential of the sum is a sum of the subdifferential, but it's almost always true. Not always, but almost. Okay. And then we just compare this term, compare that term, and compare this term. Under this condition, we can, and do the comparison, we'll have Pf plus G. It's going to be Pf compose Pg. Okay? So basically, this is a theorem. If we have two functions, of course, you can extend this to more than two functions. But for simplicity, if you have two functions, if you satisfy this naive condition here, you can decompose the proximity operator of the sum into the composition. And the proof is just compare the optimality conditions, nothing fancy. And you might suspect, how useful is this, right? I mean, it's such a simple result. How can it be any useful? Well, so that's why. So let's see two examples. Okay. And see how we can use that condition. And this condition is a sufficient condition. Okay, not necessary. It's almost necessary, but not quite. So let's see a quick example. How can you actually use this naive sufficient condition to get interesting results? So I will. So the first observation is in machine learning, when you derive a regularizer. A regularizer is usually a norm. Okay, if it's not a norm, it's a semi-norm, or so in other words, a positive homogeneous function, right? So let's take a regularizer G. Let's say it's a norm. Okay. So now this sufficient condition asks us to look at the subdifferential of the function G, right? Subdifferential of G. So I have a norm. So what information can I get for its subdifferential? Well, it's a norm. You can show the subdifferential of a norm at any point Z is the same if you scale it. Okay? So essentially, if you have a norm, you take a point Z, and if you scale the point, it's just a positive scaling of the point Z, you don't change the subdifferential. This is kind of obvious because the norm is positive homogeneous, right? If you scale a vector, so this is essentially, this is a one homogeneous thing. This says this is a zero homogeneous thing. Okay? So this one is invariant under scaling. This is a linear thing under scaling. So because take the derivative, you get from one homogeneous to zero homogeneous. You can prove this is actually an if and only if condition. Okay, so I have a norm regularizer. This is the only information I can have from the fact that it's a norm. So now I need to satisfy the sufficient condition, right? So what I want, so this is what I want. The subdifferential of G of Pf of Y is going to be contained subdivision of Y. And this is what I know. This is what I want. Well, the next obvious thing is if Pf of Y is proportional to Y, in other words, if Pf of Y is lambda times Y for some lambda, okay, then I satisfy this, right? Because G have this property. If Pf of Y is lambda of Y, this is lambda of Y, then I not only have this containment, I actually have equality there, right? So if I have this condition, I will satisfy sufficient condition. Therefore, I will have this decomposition rule here. So what kind of function will give me this property? Kind of function F, if I apply its proximity operator, it's just a scaling. What kind of function is that? Well, we can characterize this. So this is a theorem. It essentially says a function f have this property pfy equals lambda y for lambda is positive if and only if the function f is going to be the increasing function of the norm, okay, where h is increasing. This is the if and only if condition. And the side result from this characterization is that, so in kernel methods, the success of kernel methods is, you project everything, you lift everything to a high dimensional space, essentially an infinite dimensional reproducing kernel space, right? You lift everything there, and then because of that nonlinear transformation, you learn a linear separator there, and then in the original space, you can have a nonlinear map. The only trouble is you lift everything to infinite dimensional space. How do you optimize it, right? It's infinite dimensional space. The reason we can still do kernel methods is because we have these regularizers that induce the so-called representer theorem. So you can restrict everything to a subspace spanned by a training data. That's essentially the success, guarantees the success of kernel methods. Quite unexpected is this actually also gives you a characterization of what kind of regularizer will give you the representer theorem. So this if and only if f gives you the representer theorem. Okay, this is kind of surprising because this is more like an analytical result. I have a regularizer, I need to have the representer theorem. And this one is more like a computational result, right? If my function is an increasing function of the norm, then the proximity operator is just a scaling. So this is more like a computational result. It actually is equivalent to an analytical property. So okay, so I'm not going to prove this. The proof is not too hard. The only trouble in this proof is you have your function f, which can be non-smooth, which can have a proper domain. Its domain might not be everywhere, can be an indicator function, and we need to deal with that. And that's the hard part, because whenever you have a function only defines not in the whole space, only in a subset, then at the boundary of your domain, the subdifferential of your function is going to be very ugly. You essentially lose control at the boundary of your domain, at the subdifferential. The key idea in the proof is you smooth the function, okay, a little bit. So essentially, it's very similar to the Morehouse envelope function you saw before. So essentially, you go from f to a smooth function, and then we can take derivative, we can do anything we want. And the nice thing is, when you do this smoothing, you don't affect these properties. These properties are preserved when you do this envelope smoothing. That's the beauty of the envelope function. So essentially, certain properties of your function will be preserved. Yeah?
When you say infinitely effective representative, do you mean that if you minimize the convex loss function over a data set,
yeah,
it's regularized by that?
Yes.
Okay.
Yeah, that's kind of what I mean. Okay, so now let's look at, again, an example. So this is, of course, this is going to be a familiar example. It's again related to Nasso. So it's called an elastic net. So when we do Nasso, one problem people realize is the Nasso, when you have multiple features, they are equally important. The Nasso tend to pick one of them or a few of them, right? And if you have an L2 regularizer, you will essentially select everything that are equally important. So that's why they propose a so-called elastic net. So the elastic net says this. So instead of using the one norm, we take the two norm and hope to get the best of two parts. We get sparsity from here, and we get the sort of the stability or spreadness from the two norm. Okay, how do you compute the proximity operator of that? The P of this is what? Well, we just use this result. So this is going to be my f. This is going to be my g. This is a norm, positive homogeneous. This is the increase function of the norm, right? So we have the decomposition. So this is going to be p of the one norm. Sorry. Squared compose p of the one norm. So this result is known before, I think, because of the separability, because these guys can be reduced to the one-dimensional case. And once you are in the one-dimensional case, you can do a lot of things. So this result is known before. However, what we realize is this one does not have to be the one norm, right? It can be any positive homogeneous function. So you have your favorite regularizer, trace norm, or whatever, you can put it here. So adding an L2 norm regularizer in your problem, computationally, is almost free. And of course, we know how to compute this. Just do a little bit of algebra. Okay, so that's a very quick application of this theorem here. And it's also, you can use that to prove this thing here. So I'm not going to do that. So I'm going to erase that. So a second result, which I don't have time to go through in details, but I can give you the result. So this is related to another part of optimization, the discrete optimization. So where you have a submodular function. Instead of have a convex function, you have a submodular function. And a useful thing is to know is when you have discrete optimization, it's like very similar to the envelope function here. We have a function f, which is non-smooth. We get the smooth envelope function. If we have a submodular function, which is a discrete function, you can lift that to a continuous convex function, which is known as the Lavoisier extension or the Shortcut integral. And then you can apply your favorite convex optimization, toolbox, right? Okay. So a second result, which is also derived from that naive sufficient condition, is this. So this is again a theorem. So if f is a short, let's say Lavoisier extension. So I don't have time to define what I mean by a Lavoisier extension of some submodular function. So you can just Google or talk to me later. So if f is a submodular function, is a Lavoisier extension of a submodular function. G is permutation invariant. It can be more general than permutation invariant, but for simplicity, let's say it's permutation invariant. So permutation invariant means if I have a vector z, if I permute its entries, they will give me the same function value. For instance, if I have a L1 norm, doesn't matter, if I permute the input. Then P of f plus g is going to be P of g compose P of f. Okay, so for any Lavoisier extension, for any permutation, you get this decomposition result. Again, the proof is very simple. It combines the characterization, of what kind of functions are Lavoisier extensions and that naive sufficient condition. And an application is this result here, because all total variation norms, you can show they are Lavoisier extensions of some submodular function. And the one norm, of course, is permutation invariant. So essentially, very immediately this does not have to be the one norm. It can be any permutation invariant function, for instance, the P norm, right? Or any other norm that's permutation invariant. So there are many others, so I don't have time to go through there. So as I said, the proof is, again, not too hard. So essentially, you use that naive sufficient condition. And here, we need a fact from representation theorem. Essentially, we need to know what kind of function. If I give you a function, how do I know it's a Lavoisier extension or not? Right? You need to characterize that. So this is a well-studied part in economics. So the submodular functions are very useful in economics when they have this risk measure, how do you measure uncertainty? They use that So they have some characterizations there. And this is also used in game theory when you have different people, they're cooperative. And of course, in machine learning, we have seen the submodular functions very often nowadays. That's why I think this result will be of some use. Okay. So I'm running out of time, so I will stop here. Any questions? No? As I said, my office is in 8110, so if you want to chat, please feel free to come. Okay? Yeah?
Those are your newspaper, like the later one.
Yeah, the later parts are in my newspaper. So the paper is on my website, which is not on CMU yet. So the paper is called On Decomposing. So on decomposing the proximal map. So as you can see, the results are actually quite easy. I mean, the proofs are easy or trivial, I would say. But the implications are kind of nice because it gives you a very short way to recover what is known, and it gives you a very easy way to generalize what is known. Yeah. Okay. Thanks. Yeah.
Something that you mentioned on the total variation one, you mentioned you could solve that using dynamic programming
Yeah.
and linear count. Do you have a reference for that? Because I haven't seen that before.
Yeah, I do. So we have the indicator. And if you know convex analysis, you know C is convex if and only if the indicator function is a convex function. Okay, that's enough for the notation. So historically, the proximity operator is developed or motivated by the following result. So we have the projection, right? The projection operator, which is defined as the projection into some set C of the vector Z is going to be defined as the arc mean, the minimizer X in the set C, where we have the norm Z minus X, norm squared. And we put a half here just for normalization. Okay? So essentially, we are trying to approximate the point Z with the point X in the set C. Okay? This is the usual projection operator. So the following theorem is well known. And I think we learned this in a linear algebra course. So let M, a subset of H, be a closed subspace. Okay. And M perpendicular is just its orthogonal complement, where x, y is 0 for all x in M. Then the following are equivalent. First, we have a vector Z. We can decompose it as x plus y, where x is in the subspace M, y is in the orthogonal complement. Okay? And then the other thing is just, x is a projection of Z into the space M. Y is a projection of Z into the space orthogonal complement. So a picture would be you have the 2D space, you take a subspace. So this is my subspace M. And the orthogonal complement would be this guy M. And you take an arbitrary point Z. Okay? And you can decompose this into a vector. This is my X. This is my Y. And of course, X plus Y is going to be Z. Okay? This is the usual orthogonal decomposition in a Hilbert space. You learn this in linear algebra course. Okay? Nothing fancy. Well, problem. So now the goal is to generalize this theorem. Okay. So first, a mild step is to do this. Another theorem. So now we're going to have, instead of a subspace, now we take a cone. Okay. K be a closed convex cone. Okay. And K, so we need a complement of the cone. It's going to be the polar, which is defined as all points y such that xy, instead of equal to 0, it's going to be smaller than 0 for x in the cone K. Okay, this is a polar cone. And if we know convex analysis, again, if this is a cone, this polar cone is always a closed and convex cone. Okay, even though K might not be convex. And then the following equivalent, well, very similar to what we have for that, for the subspace. First, we can decompose Z as x plus y, where x is in the cone K, y is in the polar cone. Okay. Second, x is just a projection onto the cone K, and y is just a projection of the polar cone Z. Okay. So who have seen this theorem before? Okay, only one or two. Okay. So this is a strict generalization of that. An example, a picture would be this. So let me draw it here. So you have a 2D space again. So now instead of a subspace, we have a cone. So a cone would be, for instance, this one. Okay, this is my K. Okay, what's the polar cone? The polar cone is you take the extreme rays and you draw a orthogonal complement here. You take this extreme rays, you get another orthogonal complement here. So the polar cone will be something like this. Okay, this is my polar cone. And again, the theorem says you take any point Z, if you project to the cone, if you project to this cone, you get x and y. And if you sum them, you get Z. Okay? So this is a strict generalization of that because a subspace, of course, is a cone. Okay, it's the best cone you can have. So now, so this is a result obtained by Moho at 1962. So after he had this wonderful result, he had the remarkable vision, to further generalize things. So instead of, going from a subspace to a cone, maybe we can go from an indicator function of a set into, an arbitrary convex function. So that's why, that's how he discovered the proximity operator. So let me state his theorem first, and then we'll define what do I mean by a proximity operator. This is again, Moho, 1965. This is a truly remarkable paper written by Jean Moho in 1965. The only downside is it's written in French, so you don't get to read this paper easily. But I mean, now you have Google Translator, so you can translate and read a little bit. So it's a really wonderful paper. It has many results, and some of these results you don't easily find in a standard convex analysis book because of maybe it's written in French. So we take a convex function. So in this lecture, all convex functions are closed and proper. The proper means the domain is non-empty functions. Okay, so they are regular convex functions. We don't consider pathological convex functions. So we take a convex function f, and we have Fenchel conjugate. Right, the Fenchel conjugate f star is just the sup. So we have a y here of x, xy minus f of x. Okay, that's the Fenchel conjugate. So essentially, any function, you give me any function f, I can do this. I get a convex then you conjugate. So the following are equivalent. So as you can imagine, it's a generalization of that. So we'll have 2 z is going to be decomposed into x plus y, where y now we have functions, so we cannot say y in some space or set, but y is going to be the subdifferential of the function f at the point x. Second, we have x is going to be the proximal operator of f at z, and y is going to be the proximal operator of f. Stop. Sorry. So we haven't defined what I mean by a proximate operator, but already you can see this the similarity between the 3 theorems, right? Okay. So we'll define the proximity in a minute, and this result will be a direct consequence of yet a theorem, again by Jean-Marco. So this theorem is very important, and we will see Pf star of z is going to be 1/2 of z squared. Okay, and we have mf of z. So I'm going to explain what I mean by these 2 functions, and then we'll apply this into a optimization problem. Sorry, this is wrong. So to remind you, every norm here is a Hilbertian norm, is a Euclidean norm. Okay, if there is no subscript, it's a L2 norm. So this is a third theorem again by Jean-Marco in the same paper. So now let's define what is a proximity operator and this function AMF here, okay? And then we'll discuss, what are the consequences of this theorem. So definition. Actually, you can already see from the projection operator. So from the projection operator, we have a constraint here. X is in some set C. Well, if you introduce the indicator function, you can say there is no constraint at all, right? X is in the space H. Well, I have an indicator function here. That's sort of the cheating way to convert a constraint problem into a non-constraint problem. And now to generalize, we just need to replace this indicator function with any convex function f, right? Well, I mean, it's a definition, so you can do this. So the proximity operator P of the function f, a convex function f, and we introduce a parameter eta here. So this one will be important in some applications. It's going to define the minimizer of x. Sorry, I should have something here. Z is going to be x in the Hilbert space, and then we have 1/2 eta z minus x. Again, this is a Hilbertian norm, okay? Plus f of x. Nothing fancy, just a straightforward generalization of the projection operator. So except we have introduced a parameter eta here. So eta is 1. We have pf1. We will denote this as pf. Sorry, I should write this one. So pf with no superscript is just pf1. So this is the proximity operator. And the function mf I wrote here, mf eta of z, well, this is a minimizer. So this one is going to be the value of the minimum. Okay? The minimum 1/2 eta z minus x. Okay? So this one is called the Moho envelope function. Why it's called an envelope function is because if you have a function f, say this is my function f, you can immediately prove by taking x to be z. If x is z, this cancels, right? It's just 0, and you get f of z. So you have mf of z is always smaller than f of z. Okay? So if this is my f, this is going to be my envelope function, m f of eta. So it's always an underestimate of my function f if we do this. Okay? So we have some immediate observations. For instance, first, this envelope function, even so, if I take a convex function, the convex function as here can be an indicator function which takes the infinity at some point, right? If it's outside the domain, it's going to be infinity. But if you look at the envelope function is always real valued. No matter what z you give me, I can always find a minimizer, and this one will give me a finite value, right? So even so, mf is going to be a real valued function, even though f in general is only a extended real valued function. Okay? And second thing is the proximity operator, instead of real valued, is going to be a h into h. Okay? It takes a vector value. It's not a real valued function. That's why we call it an operator instead of a function. Okay? So the m is a real value, so we call it the envelope function. Pf is h value, so we call it, the proximity operator. Yeah. Which one? Envelope function? Yeah. Oh, okay. Envelope? Sorry? Yeah.
So this is about the proof that the envelope function is the lower bound on f of x because
Yeah.
m is a function of z,
Yes.
and so basically the argument that it's equal to f of x plus something.
No. Just, this is a minimum of all possible x. So here I just take x equals z. What I get from here is just f of z. Because I'm taking all possible x. Therefore, this one is absolutely smaller than that. That's why this is smaller than f of z. So if you draw a function f as a function of z, then mf is going to be, underestimated. That's why. So this is always an underestimator. And already you can see, if you have a function f that can take infinite values, mf will not. Generally, it only takes, a finite value. So this is some form of a smoothing effect, which you will see later. Okay. Another observation is this norm here. So if you know convex analysis, you know this norm squared is strictly convex, right? Which means the minimizer is unique. For any z, it is a unique minimizer. That's why I wrote equals to the minimizer. It's not, you cannot have multiple minimizers. So this one is uniquely defined. So for any z you give me, I can find an x which minimizes, and I can find only one x that minimizes that. Okay? So very simple. So now the next thing we do is, what is the minimizer? Well, we know we just take the derivative of that, right? You take the derivative of the minimization problem, you get x minus z. If x is a minimizer, we get x minus z plus the derivative of f, which is a self-differential of x, and 0 has to be there, right? And this, if you rearrange, you get z is in x plus subdifferential of x. And if we introduce the identity of map, so the identity map from h to h just sends x into x. Okay? Then you have z is going to be id plus the subdifferential at x. Therefore, x is going to be the inverse map of this at z. Okay? That's why you will see people sometimes will write this as the proximal map, proximity operator. Okay? So I missed the eta here. So that's why you see people sometimes write the proximity operator as, the identity map plus the subdifferential and take the inverse. Okay, here's an example. a familiar example. So we take the absolute value. F is the absolute value. So for more generally, you can consider this is an L1 norm, okay? And what is the envelope function, or what is the proximity operator? Or you can do the calculations because it's just one-dimensional. You take the derivative, and you try it a few times. You will get the proximate operator is going to be 1 minus eta divided by, so at that point z times z. And the envelope function it's going to be a little bit complicated. But if we draw a picture, it will be very clear. So here is when z is small, here is otherwise. So this is the formula for the absolute value. So if we draw a picture, let me draw another one. So this is the absolute value. And the proximate operator is essentially this. You take this is eta. This is eta. So if everything bigger than eta, you will do. If everything bigger than eta, it's going to be this. Do I have another color? Yes. So the proximate operator of the is this. Everything bigger than eta is a linear growth. Everything smaller than it truncates to 0. And everything bigger than eta, you get the linear growth here. So that's why you use the L1 norm. You get sparsity. Anything was smaller than eta, it will be truncated to 0 in the proximity operator. And the other thing is the envelope function. Well, the envelope function is a quadratic here. So it's going to be a quadratic function. And then grows linearly. Okay, sorry, my bad drawing. And this is known as the Hilbert's function in robot statistics, because you have a quadratic inside and outside it grows linearly. Okay, and the other thing is, as eta becomes smaller and smaller, as eta becomes bigger, you will have the quadratic function, right? But so the width here is controlled by eta. So if eta is big, the envelope function will become a quadratic function. Or if eta is small, then you'll converge to the absolute function. So eta controls how bad the envelope function, or how we can approximate the function f with the envelope function. Okay. So that's the example, the basic definition of the proximate operator. Okay. So now we can easily prove the theorem I showed before. Yeah. So it's not exactly the proof that I'm going to give for this theorem, because we will need basic facts in convex analysis. Okay, you need to assume these facts. Otherwise, it's not going to be trivial to prove this theorem. Okay, the proof is if you are willing to assume, you are willing to take results from convex analysis. This one is not too hard to prove, because let's just prove this one here. Okay. So let x be the proximate map of f at the point of z with respect to the function f. Then what does this mean? Well, we have this here. Okay, if x is pf z, then it has to satisfy this relationship. Therefore, we have z minus x is going to be in the subdifferential of x. Right? That's just the definition of the proximate operator. You take the derivative. This is true if we only if this is true. And then what you do is you and this is true if and only if x is in the subdifferential of the conjugate function at z minus x. So this is a fact from convex analysis. So x in the subdifferential of f at the point of y. So x is in the subdifferential of f at the point of y if and only if you swap the role. So y is going to be in the subdifferential of f conjugate at x. Okay, that's a fact from convex analysis. So if you assume that this is true if and only if this is true, and then we just do this. So you just remove x to the right hand side, you will get this is true if and only if z belongs to z minus x plus z minus x. Okay? Well, nothing fancy. This they will cancel, and if you move to here, you get that. So it's nothing fancy. And now we see that z minus x. So this is true. According to the definition of the proximal operator, this is true if and only if z minus x is the proximal map of f star at the point z. Okay? But we know here, therefore, so this, what is x? X is the pf of z. You remove the right-hand side, you get this equality here. That's why you get this pf z plus pf star of z equal to z. Okay? As I said, if you assume this fact, it's not too hard to prove. Yes? Which one? This one? So this, if this is true, if and only this is true, right? Because z will cancel, and then you move x to the outside. Yeah, nothing fancy, just algebraic manipulation. Yeah. So that's why this is true. And for this one, similarly, you can prove that. And the fact you will need is another result from convex analysis, which is also easy to prove. So f of x plus f star of y is going to be bigger than x of y. Okay? And equality holds if y is in the subdifferential of x, or equivalently, x is in the subdifferential of f star f y. Okay? This is called the Fenchel-Yang inequality. So if you use this inequality, you can easily prove the next thing. Okay. So now, since we have this nice theorem, we can do a small application in machine learning. Which should I use? Yeah. This one is very easy. So essentially, let's look at. So we have computed how to compute the proximal map, proximity operator of the absolute function, right? So it's essentially the one norm. We know what is P one norm. Okay, it's right in here. It's essentially the shrinkage operator. So now let's compute the projection onto the set C. Okay, where the set C. So I should write IC. The set C is just the unit ball of the L1 norm. Okay, C is just the unit ball of the L1 norm. You want to project to the unit ball. You want to project. So how do you compute the projection to the unit ball? Well, use this theorem there. Okay, the PF plus PF star is going to be the identity. So the projection onto this function is going to be the identity minus P of IC, the conjugate function, the Fenchel conjugate of that function, right? You compute what is the Fenchel conjugate of this indicator function. It turns out to be the dual norm, right? The dual norm of that. So it's going to be, so this is going to be identity minus the proximal map of the infinite norm. Okay? How do you compute the proximal map of the infinite norm? Well, it's a little bit tricky, but not much. I mean, you can work out the details. So this is just one application of that. So essentially, if you have two functions, f and f star, sometimes it's easier to compute the proximate of f, sometimes it's easier to compute the proximate of f star. But they're equivalent because of that theorem, right? You can just do whatever is convenient. And this one actually, 5 or 6 years ago, you can wrote a paper, I think on paper. You just do this, okay? But nowadays, no. Okay, so that's just one small immediate application of Mulhouse theorem. So there are a couple of facts about the proximity operator and the Mulhouse envelope, which of course I don't have time to prove all of them, but I will just mention them, and we will use some of them later on. So as I probably hinted here, we have the envelope function, which is controlled by parameter eta. As eta gets smaller and smaller, you will have the impression that this envelope function approximates my original function f, better and better. Okay, this actually can be made rigorous. So you can actually prove the following. So it's again a theorem. This theorem is not due to Mulhouse, but it's a nice theorem. Mf of eta converges to the function f pointwise as eta goes to 0. Well, if you look at the definition, it's quite clear. Where's the definition? So here. So if eta goes to 0, this one will become very, very big, right? And in order to minimize the whole thing, I'm better off, just put x equals z to cancel this bigger thing off. That's sort of the intuition. But in order to make that rigorous, you need another work to do. So that's why I'm not going to prove this thing here. Moreover, a very nice thing is if f is actually a Lipschitz function, is a Lipschitz continuous function, then the convergence is not only pointwise. Okay, the convergence is uniform. This is very important. So by uniform, I mean if you take sup of all possible x in the space, then mf eta of x minus f of x takes the absolute value, goes down to 0 as eta goes down to 0. Okay? So this is a much, much stronger statement. Essentially it says if I have my function f, I have my envelope function, then the maximum gap goes down to 0. So essentially the approximation is much, much better. And from here you can see, if I have an ugly function f, if somehow I know it's Lipschitz continuous, then I can approximate this function with this nice envelope function. And as you will see, the envelope function is going to be differentiable. It's going to be a nice, smooth function. And the approximation is uniform. Therefore, we don't lose much, right? Because it's a uniform approximation. We can make the approximation arbitrarily good. Okay. So this theorem I'm not going to prove. This part is not too hard to prove. This one needs some work. Okay. The next thing is what I have said. This envelope function is actually differentiable. It's a nice function. So the function is differentiable. Moreover, it's not only differentiable, its derivative is 1 over eta Lipschitz. So later on, when you study the convergence of the proximal gradient algorithm or many other algorithms, you'll see the gradient, if the gradient is Lipschitz continuous, that gives you a lot of information, and you can use that to prove convergence rates. So here we see for an arbitrary function f, if you compute its envelope function, you automatically have a Lipschitz continuous gradient. Okay, this one automatically has a Lipschitz continuous gradient. And the derivative of this has an explicit formula. Okay, it's going to be the identity minus the proximal map of F. It's going to be proximal map of F star. Okay, this one follows from not here. This one follows from again this theorem. Okay, and for this one, for this equation here, it follows from the definition actually. Not too, well, it's the proof. If you want to have a rigorous proof, you need to do more work. But if you just want to know why, if you look at here, this definition, if you take the derivative of z, you can ignore this mean. Okay, take the derivative, and then that gives you this formula here. Just ignore the mean there. You can get the, and you can make this rigorous why you can ignore the mean minimization there. Okay, and the last thing is, I have already mentioned, since this one is Lipschitz continuous, you can show the proximal map is contraction or non-expansion, which is not important to us. Okay, so now what is the application of this in optimization? When you want to optimize the function, why do I care about the infinite function? Why do I care about the proximity operator? Well, this is so that's why we need this result. For any parameter eta positive, x is a minimizer of the function f if and only if x is a minimizer of the ambient function. Okay, if and only if x equals pf eta of x. Okay, what this says is if we have ugly function f, you want to find its minimizer. What you can do is you first compute the ambient function, which is a smooth Lipschitz continuous, which is a smooth function whose gradient is Lipschitz continuous. You have a lot of ways to deal with this ambient function. And moreover, the ambient function preserves minimizers. Okay? You don't change any minimizer if you go from f to the ambient function. And this says I have a proximity operator, which is a non-expansion. And this equation essentially says if I repeatedly apply this operator, any fixed point is going to be a minimizer of my function f. And this is the if and only if condition. And later on, when you study the proximal gradient algorithm, you will see this is a basis for many algorithms. So you just repeatedly apply the proximity operator and hope you will converge to a fixed point. And this fixed point will going to be a minimizer of your function. And the proof of this is quite easy, actually. So essentially what you need to do is x is the minimizer if and only if 0 is in the subdifferential. Okay? X is the minimizer of that if and only 0 is the derivative of MF. Sorry. Okay? And then you can show this one is equivalent to that, and everything is equivalent. Just use this. Nothing fancy. Pretty trivial. Okay. Yeah. So in order to compute the gradient of the ambient function, you need to compute the proximity operator of the function f. Okay? So in some sense, the ambient function and the proximity operator are in something equivalent. So if you know the ambient function, you take the derivative of that ambient function, you will get the proximity operator. Okay, that's this result. That's basically what this result says. On the other hand, if you have the proximity operator, if you have the minimizer, you just plug into this formula here, you get the ambient function. So that's why the proximity operator and the ambient function, they have a 1-1 correspondence. Okay, you can make that rigorous actually. Okay, so a final thing I want to mention is it's not going to be used directly here, but this is a result I think everyone should know. But unfortunately, you don't see it in, for instance, Rockefeller's convex analysis work. So let's just state it here. So for any convex function, again, the following are equivalent. The first thing is f equals g plus some universal constant, say 1 or 2, okay? The second thing says the subdifferential of f at any point is a subset of a subdifferential of g at any point x. Okay? This one is familiar, right? In calculus, what we say is f is going to be a constant plus g if the derivative of f is going to be the derivative of g, right? Here, we actually get a loser condition. We only need the subderivative to be a subset of that. But this actually implies you have equality here, right? Okay. The third thing is the proximal map of f. At any point, it's going to be a proximal map of g at any point for all z, okay, for all either. This one is, in my opinion, is very important because it essentially says if you give me a convex function, I go to the proximity operator. There is no loss of information. Essentially, this is a 1-1 correspondence up to a constant. Okay? You give me two convex functions. They will give me the same proximity operator if and only if the functions differ at most by a constant. And the importance of this is the following. Suppose you have your problem, you have in any application, you want to design a regularizer for your problem. Okay? So how do you design your regularizer? Well, for instance, if I want sparsity, how do I come up with a regularizer that promotes sparsity? Well, one way is to look at the proximity operator. You design a proximity operator that gives you some sparseness, okay? And then immediately you know there is a function f. So you don't need to go for the function f. You go directly for the proximity operator. So that sometimes will give you some freedom. Okay. So this theorem again, believe it or not, in the same paper by Moho. 65. The proof is not too hard, but I will not do it here. Okay. So I mentioned when we discussed the envelope function, if I have an ugly function f, I don't know how to deal with that, maybe non-smooth, have singularities, I can just pass to the envelope function, which is a differentiable nice function, right? And then I can apply whatever tool I have for convex optimization. However, this is a catch. The catch is this. When I minimize the envelope function, I will need to be able to evaluate the function. And in order to evaluate the envelope function, I will need to solve this problem, okay? If I want to evaluate the function, I need to solve this minimization problem. Essentially, I need to compute the proximity operator. This can be as hard as minimizing the function f directly. So do we really gain anything by passing from the ugly function f to the smooth envelope function? Well, in this setting, it is not, because we need to compute the proximity operator, which can be as hard as computing minimizing the function f. So this idea is first realized in Martinez and Rockefeller's proximal point algorithm. Well, if you look at the original papers, you will realize these papers give you theoretical insights, but you cannot apply them in practice because of this chicken-egg problem. However, there is a setting where replacing a function f with a Moho envelope does give you interesting results. This is known as the smoothing trick. Many people attribute this to Yuri Nesterov, but the fact is, in convex analysis, they use this even in the 70s, so much longer before Nesterov. So the idea is this. Okay, where should I erase? So we don't need the proof. We don't need the proof. This is not right. So this is where this theorem is where we need. Suppose you are going to train, say, a support of vector machines. You have your hinge loss function, right? The hinge loss is of course not differentiable. Sorry, it's not here. Right, this is the one. So you have your hinge loss, which is not differentiable at this particular point. It's very annoying. So you have to use a subgradient method. However, what you can do is to apply this theorem here. Okay, this is my hinge loss. This is my function f. It's non-smooth, but I can just use the ambidextrous function to replace my hinge loss, and this will essentially do a quadratic smoothing here. Okay, that gives you a smooth function, and you can compute this ambidextrous function analytically, so there is no chicken egg problem. And you can apply the problem. And because of this theorem, because the hinge loss, you can prove Snippet is continuous. Therefore, if eta is small, this ambidextrous function is almost the same as the original hinge function. So there's no difference, minimizing f or minimizing the ambidextrous function. Therefore, in order to minimize the hinge loss, we can just minimize the smooth, nice ambidextrous function. That's one way. That's one application where this ambidextrous function is useful. This is sometimes called the smoothing trick. Okay. All right. So now let's move on to